In this video, we're going to take a look at implicit differentiation. Implicit differentiation is usually used when we have an implied function. So it's not necessarily a function, but we can look at one piece of it to satisfy a function. For example, x squared plus y squared equals 25 is a circle. If we solve for y, we'd have plus or minus, not a function, but we can always choose which half we're looking for. Now, the explicitly defined y equals here is a little more challenging, requires a chain rule, it's a little messier. Implicit's going to be easy. It's just going to be an application of the chain rule. So let's take a look. We have x squared plus y squared equals 25. We're simply just going to ddx both sides like we normally would. And in doing that, the derivative of x squared is simply 2x. The derivative of y squared is 2y, but wait, since we're taking the derivative with respect to x and it's of y, and we understand y to be a function of x, we need the chain rule. That's the inner function y, so we simply multiply by dy dx. And we do have to take the derivative of the right-hand side as well, which will be 0. And it won't always be equal to a constant, but if it is, it'll simply be equal 0. Now we simply solve for dy dx. And in doing that, we'll have dy dx equals, we would subtract 2x, and then we'd end up dividing by 2y, and this is going to simplify to simply negative x over y. And some other problems will be a little more involved, so let's take a look at what those extra steps might be. So after you ddx both sides, you're just looking for where the letters don't match, right? So different variables. And if you see that, you're going to be applying the chain rule. We get that little kick at the end of multiplying by dy dx. Then we're going to collect the dy dx terms to one side if they're not already there. And it may require some algebraic simplification, distributive property, combining like terms, and so on. Then we simply factor out the dy dx if it's necessary and solve for dy dx, usually by dividing. And we can see for right here for the circle, if you have dy dx equals negative xy, it tells us a few things that we're going to be able to apply to some more complex problems. So you can see if we're looking for when dy dx is equal to 0, that's going to be when the numerator is equal to 0. So in this case, it's when x equals 0. And that happens at the top half of the circle here, and again at the bottom half of the circle. So that makes a lot of sense. And if we're looking for when it's undefined, it's when the denominator is equal to 0, or in this case, it's simply just y equals 0, which happens at two locations, here and here. And you can see we'd have a vertical line would be tangent, so that's where the slope is undefined. And we can solve for the typical things. For example, if we had to evaluate dy dx, evaluated, let's say at the point 3, -4, because we can see that's a point on the circle with a radius 5. And we want to find that slope or the equation of the tangent line, we simply substitute in. So we'd have negative, and here we have 3 over -4. So we end up with a slope of positive 3/4. So we can do everything we've done with other derivative applications with implicit functions. Let's go ahead and dive into some examples that could be a little more involved. We're going to use our typical steps. So step 1, we will always ddx the entire equation. And in doing that, we have x cubed's derivative is simply 3x squared. Here, notice xy, the derivative of 3y of y cubed is 3y squared. Letters don't match. Multiply by that kick at the end. Minus, now we have a little more involved work here. You see that we have a product rule. We have x times y, the constant 4 I'm going to leave out. And we're going to have to go ahead and find the derivative of xy. So the derivative of the first times the second plus the derivative of the second times the first. And in doing that, the derivative of x is simply 1 times y, and derivative of y is dy dx times x. And the right-hand side, of course, is simply 0. Now, the derivative of xy is going to happen quite often, so it's nice to just know this. So from here on in, hopefully you can see that as y plus x dy dx. This is worth knowing, all right? So let's mark that down. So let's continue. Simplifying this, we have 3x squared plus 3y squared dy dx. Minus, we'll distribute this 4. We have minus 4y minus 4x dy dx equals 0. And that minus sign is something to watch out for. Common mistake, people forget to distribute it. So we're going to go ahead and collect the dy dx terms right here, and we'll kick these other terms off to the other side. And that means we're going to have 3y squared dy dx minus 4x dy dx equals, we'd have 4y minus 3x squared. And we simply factor out that dy dx. And when we do that, we're left with 3y squared minus 4x as the factor equals 4y minus 3x squared up here. And the final step is to solve, so we simply divide both sides by that factor, and we'd have over 3y squared minus 4x, and we are left with our derivative of that curve at any point. Next example involves a little bit of trig here, but again, the steps are the same. We just look at that entire equation and we ddx it. And you'll notice again we have a product rule, so we're going to go ahead and use that. So the derivative of the first times the second plus the derivative of the second times the first. So we'd simply have 1 times the sine of y plus the derivative of sine of y is cosine of y, but again, letters don't match, so we'll have that little kick of dy dx there, and then times x. Minus y squared's derivative is simply 2y, again, times dy dx, and the derivative of a constant will be 0. So let's go ahead and clean this up a little bit, and we'll keep the dy dx terms right here on one side, and we'll kick that sine y over. So we're going to have x cosine of y dy dx, just to change the order a little, minus 2y dy dx, and that will be equal to our negative sine of y. So again, same step. We see dy dx, we just go ahead and factor that out. Dy dx times x cosine of y minus 2y equals our negative sine of y. And same last step, we're just going to go ahead and divide both sides by x cosine of y minus 2y. And that will leave us with our final answer of negative sine of y over x cosine of y minus 2y. Example 3, a little more trig, a little more involved. So again, same first step, not going to change that. We're going to ddx both sides. And we're going to notice here we have the derivative of cosine of something. So remember, this is a chain rule. So the derivative of cosine of something is simply negative sine of that something. So in this case, xy. And then we're going to have to take the derivative of xy. So I'm not going to do that. I'm just going to write down a little reminder. I'm going to go ahead and take that derivative, and I'm just going to follow the rest of this problem through. So I have minus sine squared of y. Realize that can also be written as sine of y quantity squared. So that derivative would be 2 times the sine of y to the first, just to be obvious. And then again, we have the chain rule, so times the derivative of sine of y, which is cosine of y, but again, the letters don't match, so times dy dx. And the right-hand side, again, simply equal to 0. So earlier we learned that if we take the derivative of xy, that's always going to be y plus x dy dx. So let's go ahead and write that down. Negative sine of xy. And right here, we can go ahead and get this answer, which we know to be y plus x dy dx. And we can work that out if we had to, if we didn't remember, and that's all right. And then here we're going to have minus 2 sine of y times cosine of y times dy dx. And I know you trig fans out there may be noticing right away that 2 sine y cos y is a double angle formula. So that may have been simplified depending on where you are and what you're doing to simply the sine of 2y. So we'll go ahead and do that. But now we have to go ahead and isolate that dy dx. In order to do that, we're going to have to do some distributing here. So if we do that, we'll have negative y sine of xy. And then we're going to distribute the x here. So we'll again have minus x sine of xy times that dy dx minus sine of 2y, if we replace that, times dy dx. And that will equal 0. Okay. So now we can go ahead and collect our dy dx terms and kick this piece here off to the other side. So why don't we get a little dangerous here, and we can simply look at our dy dx terms and we can factor that out right away. So we know those two terms are going to have dy dx, and we're going to be left with negative x sine of xy minus sine of 2y. And that's going to equal, we added that term to the other side, so we'd have equals y sine of xy. And our final step is just go ahead and divide. So we're going to be left with dy dx equals y sine of xy over negative x sine of xy minus sine of 2y. And we'll do it like that. And then realize these negatives could be factored out. We could put a negative in front. It all depends how you really want it written. For our fourth example, we are going to go ahead and take a look at the second derivative. So our steps aren't going to change at first. We're simply going to take the derivative of both sides. And some of you may recognize this is the equation of a parabola, a sideways parabola you might call it. So we'll end up with 2y times dy dx. Again, letters don't match. Right-hand side is nice. It's just 2x plus 3. So dy dx is simply 2x plus 3 over 2y. But now what we need to do is we need to take that derivative with respect to x one more time to get the second derivative. And in doing that, we'll have the second derivative of y with respect to x. And that equals, and we have to go ahead and use the quotient rule here. So for the quotient rule, we have the derivative of the top, 2, times the bottom, minus the derivative of the bottom, which will be 2, dy dx, and we'll have to substitute for that in a moment, times the top, which is 2x plus 3, all over the bottom squared. So this is where we need to do something a little different. So we know that dy dx is equal to 2x plus 3 over 2y. So we're going to go ahead and substitute that in. So we have 4y minus 2 times our dy dx, which we said was 2x plus 3 over 2y, times, and again we have 2x plus 3 here, all over the bottom squared. Now we do have to clean this up, and in cleaning this up, we should note that there is a fraction within a fraction, a complex fraction, so we need to clear that. So we'll multiply both numerator and denominator by that fraction 2y, that denominator, and that'll cancel one term and we'll distribute it to the other. So let's see what we get. So distributing the 2y to our first term, we have 8y squared, and then we're going to have minus 2. That 2y is going to cancel out. It's going to leave us with 2x plus 3 times 2x plus 3 all over, and 2y times 4y squared is going to give us 8y cubed. So now we're going to keep going. If we clean this up, just notice we're going to have 4x squared. We're going to have plus 6x, which is plus 12x plus 9. So we'll have 8y squared minus 2 times all that. So we'll have 8x squared minus 24x minus 18 over 8y cubed. Now we could be done, but if we went back to the very beginning and took a look at this function, it was y squared equals x squared plus 3x. Let's write that down. We knew that y squared equals x squared plus 3x. It's actually hidden in here. So you'll notice with these two terms right here, if you factor out the 8, negative 8, we'd have x squared plus 3x. So x squared plus 3x can be replaced with y squared. So if we do take this one step further, we have 8y squared minus 8, and this is where we make our substitution of y squared, and then minus 18 all over 8y cubed. So now you can see you have 8y squared minus 8y squared, so we're left with negative 18 over 8y cubed for a complete simplification for the second derivative, which will help us determine concavity and tangent lines if they're overestimates or underestimates for applications. I hope that helps.